Hi, my name is Caleb Ziegler. I'll be talking about the Nanosatellite Optical Downlink experiment. I'll refer to that as NODE. Professor Cahoy is leading this project. So the problem exists where you have sensor capabilities that are greatly exceeding our ability to get the data down. Generating large and large amounts of data with hyperspectral imaging, which is multiple wavelengths are captured with these images. And with videos, high definition videos, just so much data is on satellites in orbit that we can't get to Earth. And there's always a need for more secure communications. We're always trying to be more secure and not have our communications intercepted. So this chart shows you the exploding growth of data generated in space. And it's projected to be multiple terabytes. So a terabyte is like a hard drive that you can buy. So like 6,000 of those are left on orbit of data that we could have for science missions to process on Earth. It's projected to be about $1.7 billion market with all of this data and people wanting to get it to Earth. And there's also, you have with radio frequency RF communications, you have these very large ground terminals and space terminals because you need these huge antennas. And it's a problem because you just can't really fit the small satellites we have now. So the solution, no, it's not more tissues and more bread. But it comes in the size of these. So you can have terminals that are the size of a Kleenex box to get you your data rates that are flying on satellites that are the size of a loaf of bread. So our proposed solution is laser communications. I'll refer to that as laser comm on small satellites. This affords you the ability that it's very compact, so it fits in a small space. It's very efficient, so you're not going to use a whole lot of power, not a whole lot of weight. You can get to orbit very cheaply. Very secure with laser communications. As I'll talk here in a short bit, the communication is very secure. It won't get intercepted. You have a lot of bandwidth, which means higher data rates. And it's unregulated, so there's less legal issues to try to get the data rates and the bandwidth that you need. And that's the laser communications payload. So think a loaf of bread. About a third of a loaf of bread is what you would use for your laser communications payload. So this is why laser communications is so astonishing. With typical RF technologies, you're going to spread all your power across the state of Massachusetts. And that's a lot of waste considering you're going to be in one little area collecting all of that energy. But say with laser communications, if you're pointing at the dome at MIT, it won't even go to the athletic fields. If we're sitting here trying to intercept this laser communications signal, you won't see it. And that also speaks to how efficient it is. Take all the power and direct it on a smaller area, and you need less power. So those speaks to two of the benefits of laser communications. The other benefit is it's unregulated. This is the RF radio frequency spectrum here. You can see everybody has their little place, and everyone fights for it, and you have to share for it. You don't get all the time. But with laser communications, that doesn't exist because there is so much bandwidth. And because it's so directed, you don't have people interfering with each other fighting for space. It's all yours. You can take it. It's kind of like the Wild West. Take what you want. So the node approach, what we want is a small satellite that's very efficient, can get 100 megabit per second data rates, so fast internet at home you can get. We want to scale it to gigabit per second, and when you scale it to gigabit per second, you're top tier, top rate with laser communications. That's what everyone wants. And we also want to provide compact and affordable ground stations that you can move around very cheap, so less than $100,000 for a ground station compared to current ground stations. In this image on your right, this is our transmitter module, and as I said, about the size of a tissue box. And this is some of our hardware in the lab. So the picture on your left, about the size of a loaf of bread, it's our laser, our amplifier, and our breadboard circuitry for the fibers. And then on the right, you see the laser, the fast steering mirror, which is pivotal to be able to point this very directed laser beam at the target you want while you get disturbances on your spacecraft. And we have demonstrated that we can send signals across the air in our lab, and we've also demonstrated that we can steer the signals with the mirror. And one really interesting piece of technology we have, probably the most interesting piece of technology, is the ground station. It is an amateur telescope by Celestron. And we're decking it out with a star camera that helps you point in relation to the stars. And also the back end has the receiver electronics, so you can sample your signal that way. And the concept of that is you could have a network of these receivers, place them everywhere, easy to transport, very cheap. In contrast to, say, a 21-meter dish that's cemented into the ground, it's not going to move. People are fighting over it. People pay a lot for it just to use it, not for the hardware itself. So that is a very promising aspect of this technology. And so to summarize everything, there's very much a need for high data rate communications. Laser communications are the future. And you see a lot of people come out with demonstrations, Lincoln Labs in particular, and that's the way satellite communications will be going. That's the way things are going. Because you get this high data rates, high efficiency, small size, and you have the security aspect that just naturally comes along with it all. And Node is hoping to demonstrate laser communications on a small satellite with 100 megabit per second data rates going to gigabit per second, being compact, affordable, transportable, and having the ground stations as well. Thank you.